Okay, welcome back to CS479, Machine Learning for 3D Data. So this is our second time to meet in this course. Can everyone see my slide and hear my voice? Is everything okay? Good. Cool. Okay, let's get started. So as I said last time, in this Zoom session, please set your name like this. So please have your both the student ID and also the full name in English, and also please match the full name with your name in the key LMS. And also please turn on the camera and then turn off the mic. Okay, is everyone good with this? Okay, and also as I said in the last time, so we actually went over with some of the logistics in this course. So if you missed the first lecture of this course, you can also find out all the materials, all the slides, and even the recording of the first lecture in the course webpage. So please check out the course webpage. And one of the important things for the course, the logistics is that so we basically have the programming assignments, and all the assignments are already released in the course webpage. So please check out that. You can also check out all the details about basically the instructions for each of the programming assignments and what you need to do and what you need to submit. And you can also check out all the deadlines for each of the programming assignment. So please check out this. And also, I also talked about how we're gonna basically distribute some kind of the computing resources. So we have the GPUs in the K-Cloud, but we are having some limited number of the GPUs in the K-Cloud. So we already distributed all the GPUs that we have in the K-Cloud to the undergraduate the students. So if you did not receive the K-Cloud GPU for the undergraduate students here, please let us know. And also for the graduate students, if you need a GPU, please let us know. And we are going to try to distribute some of the GPUs there. And also, if it's the first time to use the K-Cloud, please check out the K-Cloud tutorial, which is also uploaded into the course webpage. And we strongly recommend you to start to work on all the things as early as possible. So it might take some time for you to basically get used to the K-Cloud environment and also all the things in the programming assignments. Any questions for the K-Cloud or the programming assignments? Yeah, so if you did not try to use the K-Cloud, please check it out. And actually, there might be some technical issues with the K-Cloud. So if you have any issues with that, please let us know so that you can start to work on the programming assignments as early as possible. And also, as I said last time, we're going to have some kind of the short quizzes during all the lectures. And even some of the lectures may start with some kind of quizzes about the previous lectures. So please be prepared. And also, as I said, what we are going to do is that we are going to also kind of calculate some kind of the participation score based on how you answered all the questions. So basically, you're gonna get the 100% score if you answered like at least 80% of the quizzes that we had. So that's kind of things. And also, as I said, the course project is the most important part in this course. So we are going to start basically make some kind of teams for the project. And the deadline for the team matching is the next Friday. So I'd like to also strongly encourage you to start to find the other classmates, the teammate for the course project. So you can basically form a team with at most 3 people, and all the team members will be basically we will get the same grade for the project. So that's kind of things. So if you don't have any kind of ideas in terms of how you're gonna basically find the teammates, we are also going to open a channel in the Slack so that you can also start to hire some kind of the teammates for your team. So that's kind of things. Any questions for the project and also the in-class participation? So especially in the case that you missed the first lecture of this course, please check out all the materials. The slides, the recordings are already uploaded in the course webpage. Cool. And so please turn off your mic. Cool. Okay, so what we discussed last time is that we briefly seen some kind of the applications of the 3D data. So there are some kind of the applications of like 3D generation. So we have seen some cases of like text generation, the image generation, and also we have seen that there is already some techniques that can automatically generate some kind of 3D contents. So the video you can see here was kind of the state of the art in terms of like making some 3D contents. And this kind of the output can be used in some many kind of graphics, AR, VR applications like Roblox or some kind of some metaverse kind of related kind of things, right? And also for the 3D reconstruction, yeah, this is also kind of the state of the art in terms of the, if you can basically take a video of any kind of the objects or the scene, then we can also create this kind of the virtual objects or scenes that are basically copying the physical the things into the virtual world. And this kind of the technique is already being used in some kind of the products by some kind of the big tech companies. So one of the example was this kind of immersive view from the Google Maps, which is basically showing the whole 3D reconstruction of the entire city using this kind of the 3D reconstruction techniques. We also have shown seen some kind of the applications, which is basically taking the 3D data as the input, not basically generating this kind of the outputs. And those kind of the 3D perception techniques could be used, some kind of the applications of the autonomous driving or some kind of the robot and the scene interactions for many kind of the robotics applications. So those are kind of the applications that we briefly discussed in the last time. And in this course, we are basically going to discuss some more kind of the basic and also kind of the fundamental techniques that can be used in many these kind of the applications. So that's what we are going to do in this course. And what we are going to do at the especially beginning of like this course is that we are going to discuss like two different types of the techniques, especially some deep learning based techniques. The first class of the techniques might be some kind of the encoders, basically that can take the 3D data as input. And obviously we are also going to discuss the other types of the techniques about some decoders, which can basically generate the 3D data as the outputs. So we are going to start all the discussions with the techniques about the encoders, basically the neural networks that can take the 3D data as the input. And at the end, after that, we are also going to discuss about all the techniques that can produce the 3D data as the output. And before we start to discuss some kind of the 3D encoders, actually, we are going to start with some discussions about the 3D representations. So basically, the question that we have here is that how are we gonna basically represent the 3D data? So that's kind of the first things that we are going to discuss in this course. Especially, we are going to discuss the 3D representations in the perspective of the encoders. Like how are we gonna basically take the 3D data to process that in some kind of the deep learning pipelines. So what would be kind of the best way to represent the 3D data? Do you have any thoughts? For the representation of the 3D data, what would be kind of the best way to represent the 3D data with some kind of numbers? So that's the kind of the first question. Do you have any answers for this? So this is like kind of one of the quizzes. Yeah. So yeah, many people basically answered with some meshes, point cloud, voxels, yeah, many things. Yeah, actually, for the 3D, the interesting aspect is that there are actually a bunch of the ways to represent all the 3D data. So if we actually think about the other data, the modalities, for example, like the text, like text can be seen as kind of the 1D sequence, right? Like if for each of these, the sentence that we have, we can consider basically like split the sentence into the multiple tokens. And there are also some very conventional ways to basically map each of the token in the sentence into a kind of some numerical vector. Then what we end up getting is that from each of the sentence, we are having some kind of a conversion into a 1D sequence with some kind of some numerical vectors, which is corresponding to each of the token in the sentence, right? So actually we can see that the text can be seen as kind of the 1D sequence. And there are some very typical way to basically handle this kind of the 1D sequence data, right? And also there are some other types of the data that can be seen as the 1D sequence. For example, like audio might be also kind of the 1D data, basically having some sequence of the information. And how about the images? Like the image might be kind of the most common the type of the data that we can see in many kind of the AI the related problems. And for the images, also the very typical the way to represent the data might be having a 2D grid, right? Like all the image can be basically represented as kind of the set of the pixels. And each of the pixels basically have some kind of the numbers, which basically representing either the intensity or the color information. So basically, we are having some kind of a 2D grid with the numbers for each of the pixels. So these are basically very typical the representations for the text and the images. And also, people also think about video. Video can be seen as kind of the 3D grid, right? So in terms of that, we are having the 2D space and also the extra, the one-dimensional, the temporal domain. So in that sense, we can see that the videos are also kind of the 3D grid. So actually having this kind of the regular structure, like having 1D sequence or the 2D grids, was kind of the key in terms of like, in the, the advance of the neural net techniques. Actually, as you know, actually the emergence of the deep learning technique actually came from the invention of the convolutional neural net. Obviously, people are not using the convolutional neural net these days, like people are using more like transformer kind of architectures these days. But if we see the beginning of the kind of like how the neural network, the recent neural network has been developed, the first was this kind of the invention of the convolution of the neural net. And to apply this kind of like convolutional the operation, the key was to have this kind of the regular structure, either having like 1D sequence or the 2D grid or the 3D grid to apply this kind of the convolutional the operations. So in that sense, like even for all the 3D data that we have, what we can do would be is that basically we can represent all the 3D data as the 3D grid. So as we have the pixels in the image domain, we can consider the case of like having the voxels in the 3D space, right? So this might be the kind of the basic idea in terms of like how we're gonna basically handle all this 3D data. So as we apply all the 2D convolution in the 2D image cases, we can also consider like applying some kind of 3D convolution for the 3D data. So this can be the first idea, right? Then what will be kind of the downside? What will be kind of the issues when we basically have this kind of like 3D convolution in the 3D case? Do you have any thoughts? So if we think about the case of like directly extending the idea of the 2D convolution into the 3D convolution to deal with some kind of 3D data, what would be kind of some downside for that? Yeah, as you said, yeah, obviously there will be some issues with the efficiency in terms of like having too much kind of the memory and also the complexity because like the complexity will basically become the cubic, not the quadratic things. And also it might take some more time for that. Yeah, and data sparsity and the inefficiency, yeah, these will be all kind of the problems. So actually the thing is that the reason that we are actually not using this kind of like some 3D voxel representation in most of the cases is actually that the data that we are typically interested in are basically not the volume data. So typically what we can deal with some kind of some 3D scanning technology is basically getting some kind of the surface information, not the volume information. So we are not gonna get in some kind of details of like this 3D scanning the technology basically it works. But basically, if we see like how we typically basically get some kind of the 3D information from some kind of the 3D scanners, it's basically like shooting some rays from the device to the 3D object and checking the intersection point between the ray and the surface of the objects, which means that we are not getting the volume information. Actually, we are just getting the surface information, right? And also for the many of the 3D some models, some CAD models that we can download from some kind of the online repositories, typically the information that we have from these kind of 3D models is also some kind of the surface information, not the volume information. So which means that like for most of the cases, we're gonna just have the shell of the objects, which is basically having the empty, the volume inside. So we are only interested in the surface information, not the volume information. So which means that if we are going to represent this kind of the 3D shapes, basically just the shell with the 3D voxels, that will be really inefficient in terms of that many of the voxels might be just kind of empty. So actually that's kind of the issue. And also, obviously, there are some applications that we might need to basically have the volume information. For example, if the scanning that we are doing is not just kind of like using some typical 3D scanners, but if we actually are using some kind of the medical imaging, the technology in terms like, for example, like CT or the MRI, those things, those will be basically the cases that we are getting the volume information, not the surface information. For those kind of the cases, obviously we're gonna need to be handle some kind of the volume information, and the voxel representation might be kind of the right representation in terms of that we really need to apply some kind of 3D convolution. But for most of the cases, for example, like in the case like when you deal with some kind of the 3D, the scanning the data or some kind of 3D CAD models, we might just need to deal with some kind of the surface information in the 3D space. For those kind of the cases, like having the volume representation might be really inefficient in terms of the many of the space might be just empty. So this is actually a kind of figure from the other paper, which is showing the kind of the how much kind of the space would be empty when you basically represent some this kind of 2D surface with the volumes, with the voxels. So as you can see, so basically for those kind of cases, like representing the 3D shape with the voxels, actually there can be multiple ways to represent the shape information with the voxels. Like one of the ways that we can represent those things might be is that like just checking whether each of the voxel is on the surface or not, right? For each of the voxels in the 3D space, we can check whether the voxel is on the surface or not. Just having the binary information. So if the voxel is on the surface, then we have the 1. And if the voxel is not on the surface, we have 0, right? So it's having the binary information. So for those kind of the cases, we can check for how many voxels we're gonna have basically the value of the 1, which means that how many voxels on the surface and how many voxels will be out of the surface. And as you can see, as we actually increase the resolution of the 3D, the volumes, 3D grid, as we increase the resolution from the 32 to the 64 and the 128, you're gonna see that actually very few number of the voxels will be just on the surface, which means that if we have the volume representation with the voxel basically representation, that will be really inefficient in terms of the many of the voxels. We just have the value of the 0, right? So this is kind of the percentage of the volume, the voxels that are basically on the surface. So when the resolution is 32, only 10% of the voxels are on the surface. And also when the resolution is like 128, less than 2.5% of the voxels on the surface, which means that many of the voxels will have the value of 0, which will be very inefficient the representation when you basically have the 3D voxels to represent the 3D shapes. But actually, this was kind of the first idea in terms of like developing some kind of the neural net architectures that can directly process the 3D data. So this was kind of the things that were basically happening in the 2015, around like 2015, then people started to discuss some ideas of like 3D convolution by representing all these 3D shapes with the quite low resolution deep voxels, like 32 by 32 by 32 for those kind of the cases. We could get some kind of the results, like for example, for some simple tasks, like the classification, but obviously it was taking too much the memory and also the time in the training, so it's very inefficient the system. And after that, what people start to see is that, well, actually, we can consider using some kind of the more like efficient the representation in terms like not having the uniform grid, but basically somehow like having some adaptive kind of resolution depending on some kind of the information, the geometry information that we have. For example, we are having the bigger voxels in the empty space or some kind of the included the regions, and also basically having some kind of the final the voxels near the regions near the boundary of the shapes. So we are basically adapting this kind of the resolution of the 3D voxels depending on the geometry information that we have. For those kind of the cases, we could make some kind of slightly more efficient the architectures that can process the 3D data. Obviously, this is making some more kind of the burden or more the complexity in terms of like implementation, because now the structure becomes quite irregular, which means that it's not that easy to apply some typical the convolution of the operations. So those are kind of some attempts to make the voxel-based kind of neural net architecture as kind of like more efficient, but which was also basically increasing some kind of the complexity in the implementations, like all the things. And there are also some kind of architectures which is also making some kind of like engineering tricks in terms like applying the convolution of the operation, not for the entire region, but only for some kind of the regions that we are having the surface information. So for those kind of regions that contain the surface regions was called the active areas. So this was kind of some engineering tricks to avoid some kind of some convolution of the operations in the empty space, but only applying this kind of the computation in the active areas in a way to make some more efficient system. But this was also still the cases like taking lots of the memory and also the computation time in the training. But those are some kind of the attempts to apply some the 3D convolution, the neural network to handle some kind of the 3D data. So this can be like the kind of like one direction in terms of representing the 3D data. What would be kind of the other ideas in terms of representing the 3D data? So especially in the case that when you already have some kind of the 2D convolution neural net, for example, let's say, let's think about some cases like at the very beginning of the history of the like recent neural net, all the things, there are some kind of architectures that can process the 2D images, right? AlexNet, all the things. So when you already have this kind of the neural architectures that can handle the 2D data, if you have some 3D data, then how are you going to basically deal with this 3D data to process that with the 2D neural architectures? So this was kind of the one direction to extend the 2D convolution into the 3D convolution. But the even more the straightforward way to apply some kind of the 2D neural net architecture to deal with the 3D data might be that we just like render 3D data into the 2D images. So if you took the computer graphics course, I mean, there are many kind of the conventional way to basically project the 3D data into the 2D images, right? So actually we can consider like even when we have some 3D shape the data, we can actually consider render this 3D data into the 2D images and basically process these 2D images, the projected information with some kind of the conventional 2D convolution neural net. And also for that, you don't need to basically render the 3D data not into a single view. Actually, you can basically render the 3D models into the multiple views. So that was also the kind of the first idea in terms of like how we're gonna deal with the 3D data. So in the also 2015, there was the work that was basically making the first attempt in terms of like rendering the 3D models into the multiple view of the 2D images, and basically aggregating all the information to do some kind of the task like the classification. So this was kind of the very simple architecture, which is directly utilizing some kind of the convolution neural net that can process the 2D image as the input. But for that, we are basically rendering the 3D models into the multiple views. And basically to assume that we are not aligning all these 3D models in terms of the orientation, we also need to have some kind of the pooling operation, right? Basically aggregating all the kind of information from the multiple views, and that information is to use the final kind of the task, which can be classification for some other the tasks. So actually this idea was quite effective, like even compared with some kind of the architectures that takes the 3D the voxels as the input. So this is kind of the comparison between the two cases. The first row in the, can anyone see the mouse point? Yeah, the first row is basically the case of like having the voxel representation to process the 3D data. And the second case is the case of like having the multi-view images to solve the classification problem. So compared to the case of like doing some 3D convolution, actually doing some 2D convolution and just aggregating all the information was more effective in terms of like getting some better the accuracy. So actually this means that like even when you have the 3D data, actually you don't need to consider using some kind of some special architectures to deal with that. Actually the simplest way to basically like render all these 3D models into 2D images and using some kind of the some conventional neural networks for the 2D images actually can be quite effective in terms of solving the many problems. Actually, this is actually one thing that I really want to tell you in terms of that. Even when you have some any kind of 3D data, you don't need to think about just directly applying some kind of the 3D specific architectures for that. You can just try to just render 3D data into the 2D images and use the image neural network. So that is really kind of the good way to deal with all the 3D data. And actually, there are also some kind of the techniques, which is basically not just like solving some problems like the classification. So basically, the classification is the case that we basically were getting some kind of the global information for the entire 3D objects. But for also some of the problems, like solving some kind of segmentation, which is the case that we are getting the information not for the entire object, but for each of the point, for each of the 3D shapes. For those kind of the cases that we are basically predicting the information for each of the point, not for the entire the shapes, what we can also do is that we can also try to first like project the 3D things into the 2D data, into the 2D images. We can basically run some kind of image segmentation with the 2D images. And also we can consider aggregating all the information from the multiple views so that we can get basically the per point information, like the labels like this. So this was also kind of the very effective, the kind of the idea in terms of like utilizing some 2D neural networks to handle some kind of 3D data. So here's the question. In the BoxNet paper above, we need to introduce notation invariance through the data measures of this. Yeah, actually, yeah, this is really good question. So the rotation invariance and the equivariance is also really kind of the important issue to deal with all the 3D data. So many of the cases for the like 3D like segmentation or the classification, we can simply like assume that like all these 3D models are basically aligned. For example, for the cases like this chair, or in the case like when you want to classify all these 3D objects, here the question is that if we have this kind of like 3D models of the chair with some kind of the random rotation, so if we basically rotate the 3D models, 3D chair in the 3D space with some kind of the random rotation, if we want to basically guarantee that the neural net still classifies the 3D models into a chair, however we rotate the 3D models, how are we going to basically guarantee this kind of the rotation invariance, right? So basically here the question is that the rotation basically invariance means that like however we rotate given the 3D data, if we want to get the same output, how are we going to guarantee that? So that's kind of the question that we have. So this is also very interesting question, not only for the 3D, but actually also for the 2D as well. For any kind of data, we want to basically achieve this kind of some transformation, the invariance or the equivariance. So we are going to get into that point in the later lectures, but for now, we are going to assume that all the 3D data that we have are basically aligned in terms of the rotation and also any kind of the transformations. But this was kind of the case that even when you have some kind of the random rotations, through this kind of like view pulling the operation, actually we also could get some kind of the same results of the classification. But we're gonna get into the point of the rotation invariance and the equivariance later. Okay, thank you for the question. Cool. So we are talking about some kind of neural architectures that can basically process the multi-view images. And this actually, as I said, this is really good idea. So when you have any kind of 3D data, what I typically recommend is just not to try any kind of some special architectures for the 3D data. You can first try to just like render all the 3D data into the 2D images and basically use some kind of the 2D neural architectures. So that can be first attempt for any kind of the application. And this kind of the application, the architectures can be actually really good, especially in the case when you have some kind of the appearance information. So when you have not just the geometry information for the 3D models, but when you also have some kind of the appearance information like the color, texture, the materials, for those kind of cases, like especially like rendering the 3D models into the 2D images and processing them can be actually really good direction to handle all this data. Obviously, the downside is that if you want to get some really good the results, basically the high accuracy, in many of the cases, we need to render the 3D models not into a single view, but into the multiple views. So typically, as we have some more images, we can actually get some better accuracy in many of the tasks, which means that actually we might need to have some lots of the images for the same object, so which basically might increase the memory and also the computation time in many of the tasks. So in the case of like this, example, like having the multi-view images for the classification, they also use the AT views of the images to just like solve the classification problem. So that's kind of the cases. Like, typically when you want to use the multi-view images, we might need to have some lots of images to get the high accuracy. So that might also result in taking too much of the memory and also the computation time. And also, since this is not the case that we are directly just like representing some geometry information, we may not be able to capture some geometric details in the images. So that's kind of also the issue. Why is accuracy over missing from in table? Oh, so yeah, so I also didn't tell you that. So there's some kind of a gray area here, some gray box here. So we also get into this. So I'm also gonna talk about like what's kind of some hidden things here. So actually, the kind of thing is that obviously the conclusion would be is that there is a better architecture, not just using handling to some multiple images, but actually handling some other types of the representation. So that's actually what we are going to discuss later. So we are going to get back to this slide again with kind of like hidden things in this gray box later. Good question. Any other questions for the voxels and the multiple images? Yeah. So yeah, these are basically very typical the ideas in terms like dealing with some kind of 3D data. Well, but obviously there are some also the other types of the representation. So the other types of representation might be the point cloud. So here, what the point cloud basically means that we are representing a 3D object as kind of a set of the points. So which might be the simplest representation for all the 3D things. So we are not having any kind of voxels or the images, but we are basically representing all the 3D shape as kind of a set of the points, even without having any connected information. So that's why we call this point cloud, just having a set of the points. So this will be the case that we are having the x, y, z coordinates for each of the point. And probably we might also have some extra information. For example, we can have the color information, or we can have some other information where we can have some kind of the surface normal information. Here, what the surface normal basically means is that if we try to basically approximate each of the local region of the 3D surface with the 3D plane, the plane normal becomes the surface normal. So basically, the surface basically normal basically means that when you want to basically approximate each of the local region with the flat plane, the normal of the plane basically means the normal of the surface. So this is kind of the first derivative information of the geometry. If we get into some more the technical things, actually we are going to get into this also as well in the next lecture. We're going to also discuss how we can utilize this kind of surface normal information to reconstruct the continuously geometry information. So that's also kind of the really important information for the geometry. But for most of the cases, for the point cloud, we're basically just having the set of the points with the x, y, z coordinates. Then the question might be is that why do we need to use this kind of like point cloud representation? Actually, this is really common representation especially for many of the cases that we are dealing with some kind of some scanning the scan data. So if you also think about like how the 3D scanners basically work, as I also mentioned in the previous slide, those are typically the cases that we are basically shooting some rays into the 3D space and basically checking the intersection points between the ray and the surface, basically the objects. So typically the output of the 3D scanning is basically a point cloud. So if we want to deal with this kind of 3D scan data, that we might need to basically have some kind of the deep learning the techniques that can directly also process this kind of some point cloud information. Otherwise, which means that we might need to first like convert all these 3D scan data into the other representation like the voxels or these multi-bit images that might be really inefficient in terms of like handling all this scan data. So basically, the point cloud is basically representation of like 3D data that are basically captured from the real things using these 3D scanners. But not only for some kind of scanning the scenarios, but also for some other kind of the applications, especially for some kind of the physical simulations in the graphics or the robotics, having this kind of like some point cloud representation can be quite efficient in terms of like running some kind of simulations in some kind of applications. Actually, the problem with the point cloud is that now we are basically losing some kind of the regularity in the structure. So in the cases that when you have the 3D voxels or the multi-bit images, basically we are having some kind of the 3D grid information or the 2D grid information with the multiple images. For those kind of the cases, we are basically having the grid structure, which means that this is really good type of the representation that we can apply the typical the convolution operation. But for those kind of the cases, we are not having the regular structure, okay, not having any kind of the grid structure, which means that we cannot directly apply some kind of the convolution neural net. So actually, that was the reason that people did not try to just like use this kind of representation to process the 3D data into the neural net, because like people did not have any idea how we're gonna basically deal with this kind of like irregular types of the data with the convolution neural net. So that's why, after that, people started to invent some kind of new architectures that can process this kind of the point cloud data. The first attempt was this PointNet, which is kind of things that we can also discuss in the next week. And implementing this PointNet is the part of the first assignment. So we are also gonna get into some more details of this architecture. But actually, it turns out that if we see some details about the PointNet, actually, this architecture is pretty simple, right? Without any kind of like some convolutional operation, the PointNet actually could work quite well in terms of solving some of the tasks with the 3D data. And also the implementation is like quite easy, and also the network is basically running quite fast. So after like introducing the architecture, actually this kind of the architectures like handling the point cloud became quite popular for many kind of the applications. So that's basically what we are going to discuss later. But obviously there are lots of kind of the downsides for the point cloud representation. What would be kind of the downside for the point cloud representations? Do you have any thoughts? Yeah, compared to the cases like having some voxels or the multiple images or some other representations, what would be kind of some limitations of the point cloud representation? Yeah, as you said, like basically we are basically losing some information, right? Because like all the geometry is just like represented as a like set of the points. The thing is that basically we are losing some information about, for example, like the surface and the topology as well. So as you can see in this like some very extreme example, like when you have like set of the points like this, we don't know whether it should be really kind of this kind of the donut like the types of the surface, or this kind of like the spring kind of the shape of the lines. So there can be some this kind of ambiguities, which means that we basically do not have any kind of surface and the topology information. And because of this like lack of this information, the point cloud, the data cannot be directly used in some many kind of the applications. For example, we cannot basically render the point cloud into some kind of images, where in terms of like manipulating this kind of data, because the lack of this kind of surface information becomes some kind of the hurdle to apply some many kind of the techniques for that. So basically, for many kind of some downstream applications, we first need to convert this point cloud into some other types of the representation, for example, like the mesh that we can also discuss. So that's kind of the limitation of the point cloud. And also to precisely capture, basically describe all the details of the geometry, we also need to have like tons of the points. For example, like to capture all the details here, we might need to basically have some like more than, for example, like hundreds of thousands of the points, or even like millions of the points. But the thing is that also for so many of the architectures that can process the point cloud data, it's not that easy to increase the resolution of the points. This because it's not easy to basically increase the number of the points, because as we increase the number of the points, there might be some issues in terms like some memory or some computation time. So that's also the same issue for the point cloud as well. So the other types of the representation for the 3D data might be also the polygon mesh. So the polygon mesh is the most common and the popular representation for the many 3D data. So especially if we see many kind of 3D CAD models, some 3D models in some online repositories, many of the 3D models that we can see in many of the some 3D data set are actually already represented as kind of 3D meshes. So these are also the most common and the popular representation. And this is also the compact form in terms of like representing the surface, because now we are not only having the points, but we are also having the connectivity information and also the surface information represented with the planes in the 3D space. So this can be the most effective representation in terms of like representing all the surface of the 3D volumes. So you can see the polygon mesh is kind of the graph structure, graph-like this structure, but it's not exactly the graph structure. So in the polygon mesh, basically we are having a set of the vertices and also a set of the edges connecting all the vertices each other. And the difference with the graph structure is that we are also having the faces, which is basically formed by basically having some kind of the set of the edges and the vertices. So we are having the vertices and the edges and the faces in terms of like having some kind of the literally the mesh over in the 3D space in terms of basically representing the surface in the 3D space. So that's basically the very common the representation of the many of the 3D data. And typically, people use the triangle mesh, which is not having any kind of the arbitrary polygon for the face, but basically having the triangles for each of the face. So that's the kind of the common representation. The issue with this kind of the polygon mesh is that basically we might want to basically define some kind of the valid meshes, but actually in most of the cases, it's not that easy to basically satisfy all the constraints for the valid mesh. So what would be kind of some kind of condition that we can consider as kind of the some validity of the meshes? For what kind of the cases, we can say that the mesh structure is kind of the broken or some kind of issues. Or what would be the cases that we can say that the mesh structure is kind of like solid in terms of representing like the surface in this 3D space correctly. The question here is that is a more abstract way that we can still think of the point cloud as a metric space, or is it just like topological space? The question boils down to whether we can have a metric or not. For example, when working with some boxes we do. So actually, also even when you have the point cloud as a metric space might be kind of the other things, but in terms of like topology, so we can also consider like somehow getting some definitions of the topology with the point cloud in terms like defining the connectivity of the points. So actually, there's kind of a whole theory about that, which is about the persistent homology things. So if you basically Google the persistent homology, what you can see is that you can basically see some kind of theory in terms of like how we can define the topology in terms of like connecting all the points based on the proximity. For example, even when you have this kind of a set of the points, actually we can consider basically making some kind of like forming some kind of edges and the faces based on the distance. For example, if the points are basically close enough, basically if the distance between the points is below this threshold, we can connect all the points, basically forming the edges. And in that way, you can also basically form the faces as well. So in this sense, actually, as you basically increase the threshold for the connectivity, you can see some kind of the different sort of the structure of the topology of the point cloud. So even you can basically control the threshold of the distance to basically get the certain some topological information for the given the set of the coins. So there's basically a full set of the some theoretical the ideas for that, which is called the persistent homology. So I recommend you to check that out. But we are not gonna get into that much kind of details for that. So we are also going to discuss some very basic ideas for that. So that was the question on the Zoom chat. And also my question here was basically, how are we gonna basically define some kind of the valid meshes in terms like forming this kind of the vertices and the edges and the faces. What would be the cases that we can say that the mesh is kind of the broken or something? Any ideas for that? Yeah, so we can basically think about some kind of the goodness of the mesh in terms of that. So at the end, what we want to do is that we want to basically represent a 2D surface with this kind of like mesh structure. And we also hope that this kind of the surface information is also forming a kind of the like the volume in the 3D space, right? So in terms of that, actually, there are some kind of the multiple, some kind of the criteria that we can think about for the kind of the validity of the meshes. Like one of the things for that might be is the kind of the manifoldness in terms of like, basically what we want to do is that we want to basically make a mesh in terms of like that every local region of the mesh can be mapped to the 2D flat plane, right? So if we think about the surface of the some 3D the volumes like the body, for example, if we think about the skins of the human body, we want to see that basically every local region of the skin of the human body can be mapped to some kind of a flat plane, right? Which means that every local region is really 2D surface, not something kind of arbitrary things. So we basically might want to basically have this kind of the constraints in terms like when you basically make some kind of the meshes. And some kind of the cases that is basically breaking this kind of the condition is, for example, this kind of the case. For example, if we have a single the edge in this 3D space that are basically having the 3 adjacent faces or more, this will be like one of the examples that this local region, the mesh, it cannot be mapped to some kind of the 2D plane. So this is kind of the case of like breaking this kind of the condition in terms of the local region can be mapped to the 2D flat plane. So this kind of the condition is called the true manifoldness. So manifold basically means some kind of the 2D surface. So which means that basically we want to make this 3D surface that can have some like all the local regions that can be basically be mappable into the 2D flat plane, roughly speaking. Or the other kind of the cases like breaking this kind of the condition might be basically having a vertex, which is basically having some adjacent the triangles, but which are basically not forming some kind of the 2D surface in 3D space, but just making a kind of the some point in the 3D space. So those are kind of some sort of the invalid the cases of like not having the two manifoldness of the 2D meshes. Where there can be some other kind of conditions. For example, we might basically want to form some kind of the 3D volume with some kind of the 2D surface. For those kind of the cases, basically we should be able to basically split the 3D space into the some inside region and the outside region, right? Which means that so the 2D surface should basically form some kind of the watertight the shape in the 3D space. So that can be one of the conditions in terms of that we are having some kind of the 3D mesh, which is basically making some kind of the volume in the 3D space, where there can be some other things in terms of that we can have some kind of the topological the constraints. We can also basically consider having all the surface normal having some consistent orientation in terms of that all the normals are basically heading the outside or inside of the shapes. So those kind of those might be kind of the conditions to check some kind of the validity of the meshes. So we are not going to get into some details for this, but yeah, so those are kind of things. And also, if you are more interested in some these kinds of more like some details about some geometry, some data, you can also check out the other course, the geometry, the modeling and the processing. So this is that is basically the course that we are discussing some more details about this kind of some geometric things. But anyway, so given this kind of some polygon demesh, what are the kind of the advantages having this kind of the mesh structure? Actually, there are lots of some advantages, like having this kind of the mesh structure. One of the good things is that now we are having the surface information, which means that now we can apply this kind of data into the many applications. For example, now we can render 3D model into the 2D mesh, 2D images. So it can be used for the 2D rendering. And we can also basically add some kind of the more the surface information. For example, we can add some kind of the color information or some kind of the material information. And this is also one of the examples that we are also adding some kind of the geometric texture, like some displacement map for each of the point over the surface. We are also adding some kind of the geometric details in terms of, like, for example, like some sort of the perturbation over the surface in terms of adding some geometric details. So we can add this kind of some texture information over the 3D the surface. Now because now we are having the 3D surface information. And also for many other some applications for the deformation or the manipulation, since now we are now having some the surface information, we can apply this kind of the techniques to manipulate the many kind of 3D data, which means that these types of the data also can be good for so many kind of some simulations. So for many kind of some physical simulation to check the collision or something else, so having the surface information also can be good. So there are actually lots of some goodness in terms of like having lots of the applications of the polygon demesh. What would be the downside in terms, especially in terms of like processing the data into this 3D neural network? So in the case that when you have the polygon demeshes, if we want to basically directly feed this kind of the polygon demesh information into some kind of some deep learning kind of the pipelines, what would be kind of the disadvantages for those kind of the cases? Do you have any thoughts? Yeah, obviously one of the kind of issues would be basically the irregular the structure. So also for the point cloud, we had the same issue in terms of that we do not have any kind of some regularity in the data. And here, while we now have some kind of the connectivity information, the thing is that this kind of connectivity may not be regular, which means that we cannot typically use some kind of the typical the convolutional the operation. So that can be kind of the one big issue in this case. Actually, there are some kind of the attempts to apply some sort of the convolutional the operation over the meshes as well. So we are not going to get into some details there. But if you actually think about like applying some typical the ideas for the convolution neural net, there will be some kind of the convolution the operation and also the pooling operation in the architectures, right? So actually, it's kind of the doable in terms of applying some convolution to operation, because still we can define some kind of some neighbor the vertices or the faces, and based on that we can try to basically aggregate some kind of the local information. But the question might be is that how are we going to apply some kind of the pooling operation, right? So if we think about like how the pooling the layer works in the 2D convolutional neural network, so the role of the pooling operation is basically progressively basically reducing the resolution of the data, right? So when you have some kind of the higher resolution the data, the pooling operation is basically making some kind of the low resolution the data while basically aggregating some kind of the local information. So the question in the mesh case might be is that how are we going to basically define this kind of the pooling operation in terms of like making some kind of the architectures like interweaving some convolution and the pooling, right? Do you have any kind of like thoughts in terms of like how we can apply some pooling operation in the mesh case? Can you kind of like come up with some any ideas in terms of like how we can define some pooling operation? So when the pooling is basically the operation that can progressively basically reduce the resolution of the data, when you have some kind of a given this 3D mesh, how we can basically do this kind of sort of the progressive the reduction of the resolution of the data. actually there are some very conventional, very traditional idea in terms like decreasing the resolution of the meshes, which is the technique called the mesh simplification, which was introduced in like 1990s. So if we see how people worked on basically decreasing the resolution of the meshes before, the basic idea for that is this like edge contraction the idea. So this was basically the case that we are basically picking one edge in the 3D mesh and basically merging two vertices, which are basically adjacent to the edge. So this is the case that we are taking this edge and then we are taking out this edge in a way to basically merge these two vertices. So we can basically iteratively decrease the resolution of the meshes by basically iterating this operation. So this is the operation that we call the edge collapse or the edge contraction. So by basically iterating this edge contraction the operation, actually we can decrease the resolution of the meshes. And actually for some kind of the mesh-based the convolution of the neural network, actually we can apply the same idea. So while we are basically decreasing the resolution of the meshes with this kind of the edge contraction the operation, we can do some kind of the pooling kind of operations. So that was basically the idea that was like first introduced in the paper called the mesh CNN. So this was the case that we are having some kind of the information for each of the edges. So for a given kind of the mesh structure, we are having some kind of information for each of the edges, and then we are aggregating this kind of the edge information with the edge contraction. So when you take out this like the edge E, we are aggregating the information of these two like the edges that are basically opposite to each other, the B and A, and also in C and D. So in this way, we are basically iteratively decreasing the resolution of the meshes. And if we also do the opposite things, like if we just do all the things in the reverse way, then we can also define the unpooling the operation. So that was this kind of the some ideas in terms like using some very conventional ideas of the mesh simplification to apply the same kind of the pooling operation to basically do make some kind of the convolution neural network that can work with the meshes. So there are this kind of the attempts in terms like making some kind of the convolution of the neural network that can take the mesh structure as the input. But obviously the implementation is really complicated. So there are lots of things that, because still the structure is not regular, there are lots of things that you need to specially handle. And also those kind of ideas were not verified that much kind of the diversity data set. So I just want to say that there are some attempts to apply some convolution neural network into the mesh structure, but this is not that common approach because of the main kind of the complexities in the implementation, also for many other things. So those are kind of things. Also, in terms like using this kind of representation, not for the processing, but also for the generation. So we're also gonna get into the point of like how we can make some like produce some kind of 3D outputs using the neural network, not just taking that as kind of input, but for the cases of like creating this kind of 3D output using the neural network. Also, the kind of problem is that it's really challenging to make some kind of the valid mesh. So we also discuss some kind of the multiple criteria in terms of like defining some kind of the validity of the meshes. So in terms of like creating some kind of valid meshes, it's also really challenging to basically satisfy all the conditions in the final outputs. And also there are some kind of the attempts to make some kind of 3D meshes directly using the neural network. And this was also the work which was introduced just like 3 years ago in the 2020. And their idea was actually quite straightforward. So actually there's already kind of some neural network that can produce some kind of the sequential data, right? Like for example, for the like ChatGPT, for many kind of the large language models, they are basically producing some kind of the sequential data as the outputs. So their idea is basically directly using this kind of some auto-regressive model that can produce some kind of sequence of the data to produce the sequence of the vertices and the sequence of the faces. So this is basically the case that we are somehow sorting all the vertices and the faces in the given 3D model in some specific way. Then we are basically producing all the sequence of the vertices and the faces using some very conventional neural net architectures that can basically produce all the sequential data. So for those kind of the cases, we can basically make a sequence of the vertices and a sequence of the faces based on that. And these were basically the outputs of the some generation. So as you can see, for some of the cases, if the output looks quite good in terms like the output really looks like some kind of the validity matches. But for some other the cases, as you can see in the red circles, you can see that for many of the cases, the output looks really bad because like when you have like very small kind of the mistakes in terms like having some kind of the wrong prediction for any of the single the vertices and the faces, we are getting some very poor the outputs, which is basically missing some, totally missing some of the big regions in the 3D outputs. So those are kind of the limitations when you basically try to directly produce all the 3D meshes using the neural network. So those are kind of some kind of the some downsides of like using the polygon the meshes as the 3D representations. Obviously, there are also more the kind of the complicated sort of kind of the representations of the many 3D data. So also the CAD representations are basically used in so many kind of the CAD applications. For example, it's not just having the meshes, basically vertices, edges, and the faces, but having some more like high level information, like some primitives, like having some cubes and the spheres and the cylinders, and also some kind of the parametric curves, some B-spline kind of things, and also the Bezier surfaces, parametric surfaces as well. So we are also not going to get into some more details about this kind of some parametric representations of the 3D models. If you are also interested in this kind of like some parametric representations, you can also check out the geometric modeling and the processing the course. So that's the course that we are also discussing some more details about this kind of some parametric representations. So those kind of representations can also be used in many kind of the applications, but typically these representations are not used for some many kind of some processing architectures, some encoding architectures, taking those things as the inputs. But we can basically make some kind of neural architectures that can produce these representations as the outputs. But obviously, the challenge might be is that how we make some of these kind of the outputs with these representation with some kind of the valid shapes. So there might be some more constraints in terms of like making some valid outputs with this kind of some higher level representations. So there might be also kind of the cases. Here the question is that has GNNs ever been used to deal with the meshes? Faces might be able to be handled by. Yeah, so that's really a good question. Actually, we can say that the meshes is kind of some extended version of the graph structure. So as we know some kind of the neural network that can handle some kind of graph structure, we can consider using these kind of architectures to handle the meshes, right? And also even for the point cloud, if it can first define some kind of the connectivity across the points based on their proximity and apply some kind of the graph neural network architectures. So that's also kind of the things that people tried. So we're going to also get into that point. Actually, the architectures dealing with some kind of the point cloud data is kind of simpler version of the GNN. Actually, also the variance of the architectures dealing with the point cloud can be seen as kind of some another version of the graph neural networks. So we're going to also discuss this kind of the analogy between the GNN and also the architectures dealing with the point clouds. So that's also what we are going to do in some other lectures. That's also a really good question. Any other questions for these representations? Cool. Yeah, so those are basically some of the representations for this 3D data. Actually, there are more, but these four might be some kind of the representative representations for this 3D data, having the voxels and the mesh, the multiple view images and the point cloud and the meshes. So if we basically see the kind of the pros and the cons of each of the representation, let's see this table. So in terms like precisely describing all the details of the geometry of the 3D data, voxels may not be good because like if we want to capture all the details of the geometry of the given the 3D data, we might really need to have some very high resolution of the voxels, which might be also very inefficient. So there might be kind of some kind of downside of the voxels. For the multi-view images, also the thing is that this is not the representation that can directly represent all the geometry. So in terms of that, see, this is also not the ideal representation to capture all the details of the geometry. But still from the multi-view images, we can also try to recover the 3D shapes. So we are also going to get into that point in terms of like how we can recover the 3D geometry from the multi-view images. So that's kind of things. Also, point cloud may not be the ideal representation in terms of like representing all the geometric details, because like this is not the representation that can have the surface information. So that can be also kind of a downside. So in terms of like geometric fidelity, the best representation might be basically the mesh. So that basically contains all the surface information. Also for the efficiency, mesh might be the best representation, right? Because we can have the minimal set of the vertices and the faces to capture all the some of the surface information. Point cloud might be okay in terms of that we can just like having a set of the points. But if we want to capture all the details, then we also need to have some more the points. So that's not good. The voxels and the multi-view images might be basically the worst representation in terms of like the efficiency. And also for some kind of the applications like rendering, obviously for the rendering, meshes might be good. Also the multi-view images are already having the rendered the outputs, so these are also the good kind of cases. But for the manipulation, if we want to basically change the shape, like if we want to basically change the articulation of the human bodies, for example, for those kind of the cases like voxels, the multi-view images and the point cloud may not be good because we are not having some direct the surface information. So meshes might be the best case for the manipulations. For the generation, actually, generating some voxel the representation is actually quite easy because we know how we can do these things for the 2D images as well. So in terms of generation, the voxels might be good, but obviously the quality of the output may not be good because of the lack of the resolution. And also for the generation, the point cloud generation is quite easy thing because like there is no constraints in terms of the validity. But if we want to make some kind of the mesh structure, obviously it's not that easy because of the lots of kind of conditions for the validity shapes. And also the regularity, this is kind of the most important part in terms like designing some kind of the some 3D encoders. So if we want to make some kind of encoders for these types of the representations, voxels might be easy because it has some already regular structure. Multi-view might be also the easy in terms of those. So it has also the regular structures, but the point cloud and the meshes might be challenging in terms of that they are not having any kind of the regular structures in the data. So it means that we might need to make some kind of some specialized architectures to deal with this kind of the point cloud data and also the mesh data. So those are kind of things. Any questions on this? Actually, there are also many other types of the representations for the 3D data. So one important representation that we did not discuss so far is the implicit representation. So this is also kind of things that we are going to discuss in the later lectures. The basic idea for the implicit representation is that now we are describing a 3D shape as a function. So there is no any kind of some explicit representation, but every single 3D shape is now represented as a function in terms of that the function takes a 3D coordinates as the input and basically outputting some kind of information like the occupancy or some kind of signed distance. For example, like we can have the volume information by having the 3D grid and having some occupancy information for each of the voxels. But instead of that, what we can have is that we can have a function that takes the 3D coordinates in the 3D space as the input and basically saying whether the point is inside or the outside, or whether the point is like how much that the point is close to the surface. So those are another kind of the types of the way that we are representing some 3D data. So the problem of like this representation is that this function representation, some implicit representation, cannot be used as kind of input to the neural net because the representation is already the function. So it's not that kind of trivial to basically take this kind of representation as the input, but still this representation can be used for the output for some decoding the architectures. So we are also going to discuss that idea in terms of like, how we can basically produce a function as the output of the neural net. Actually, this is the case that we can achieve the quality of the outputs in 3D generation. So we are going to get into that point. And also what we are going to do, actually, so we only have the 5 minutes today, but for the next lecture, what we are going to discuss is that how we can also convert like one representation to the other. So before that, one point here is that apart from the multi-view, don't all the sensors produce point cloud? Don't you assume there is some post-processing for the meshes when they are about the fair comparison? Yeah, actually, so there might be some kind of cases, like for some of the cases, for example, that we are dealing with some kind of the scan data, some raw scan data, the input data might be the points, right? But for some of the other cases that we are dealing with some kind of 3D CAD models, the data that we have might be basically the meshes, right? So depending on the problems and depending on the data that we have, actually we might need to use some kind of the different the architectures that can deal with either the meshes or the point clouds, or we can consider doing some kind of the conversion. So even when you have some kind of the mesh data set, we can convert all the meshes into the point cloud and use some kind of architectures that can process the point cloud data. Or even when you have some kind of the point cloud data as the input, for example, for the scan data, we can consider like converting all the point cloud into some other representation into the meshes or some implicit representation in a way that we can utilize this data set for some kind of some applications, for example, for rendering or some manipulation for many things. If we are taking the point cloud as input, we basically might need to convert this point cloud into the other representation. So this is kind of like very important part in terms of like dealing with the 3D data set. Even when you have some kind of the meshes as the input or the point cloud as the input, how we can basically convert this representation into the other representation in a way that we can utilize all this data into some some other applications. So that's basically very critical things in terms of like many of the geometry, the processing the problems. So let's think about like how we can basically do some like all the conversion across all the representations. So how can you convert the implicit function into the voxels? This might be the easiest way, right? So given any kind of the function that is basically checking like given any kind of 3D coordinates, we can say whether the point is like inside or the outside of the 3D shape. If we have this kind of a function, then how can you convert this into the voxels? This is quite straightforward, right? Because we can just like evaluate the function in a way that we can basically fill all the voxels in the 3D grid, right? So this is the kind of very easiest kind of conversion from the implicit function into the voxels. How about from the mesh to the point cloud? How can you basically generate the point cloud from the meshes? This is also very straightforward, right? We just need to sample the points over the surface. So this is just a matter of like just sampling points over the meshes. So this conversion is also very straightforward, right? So the conversion might be is from the mesh to the multi-view images, which is also very straightforward in terms of that we just need to render all the meshes into the 2D images, 2D planes. So if you took the computer graphics course, like the rendering is basically very typical things, right? So this kind of conversion might be very easy and very straightforward. The problem might be in the conversions, for example, from the voxels to the mesh, how we can convert the voxels into the mesh, right? So if we can also have this connection from the voxels to the meshes, we might need the other way around. So now we can see this kind of sequence from the implicit function to the voxels to the meshes and the meshes to the point cloud. So which means that we can do this kind of sequential kind of conversion from the implicit function to the point cloud. And then the question might be is that how we can also do the other way around when you have the point cloud as the input, for example, like some scan data, how we can convert this into the implicit function. So if we can basically make this kind of bridges from the voxels to the meshes and the point cloud to the implicit function, which means that we can convert like one representation to all the other representation, right? So we are basically making a loop from the implicit function to the voxels to the meshes, mesh to the point cloud, and point cloud again to the implicit function. So if we can make this kind of loop, then we can do any kind of conversion from any representation to the other representation. So this is kind of the crucial things in terms of that we can basically change the representation of the 3D data to whatever things that we want to use. So if we can make like these two bridges from the voxels to the mesh and the point cloud the implicit function, then we can do conversion from any representation to any other representation. So these two things are that we are going to discuss in the next time. So next time we are going to discuss these two ideas, like converting the voxels to the meshes and also the point cloud the implicit function in a way that now we can do any kind of the conversion from the one representation to the other representation. And then we're going to start to discuss the basic idea in terms of like processing this 3D data as the input in the neural network. So that's it for today. Any questions for all the 3D representation? Is there a generation using point cloud and change it to mesh in the rendering? Yes, actually there is a work like generating point cloud as the output and also converting that into the mesh for the rendering. But actually the thing is that we will see that point cloud can be good representation for encoding to process the data as the input. But the point cloud may not be the ideal representation to generate the 3D as the output for the generation of the tasks. Actually, for the generation of the task, the ideal representation is the implicit the representation, because from the implicit the function, we can basically capture all the details while also changing that representation into any other representations. So we'll get into that point, like what's the kind of the best representation for each of the tasks. Any other questions? Cool. So we will get into the point of like some representation, the conversion the next time. And then after that, go one more question. Can you quickly render point cloud without knowing the surface beforehand? Yeah, actually, that's also a good question. There are actually some well-known techniques in terms of like how we can render point cloud directly without having the surface information. So that's the idea that people call like subfill representation. It's not a representation, basically rendering the point cloud directly into the images. And for that, typically, so the basic idea rendering the point cloud is to basically represent every single point as kind of the small disk in this 3D space. So it's also the same as kind of like we are defining some kind of the radius for each of the point, and basically, represent each of the point as kind of a small disk, where you can actually represent each of the point as the small sphere in this 3D space and render that into the 3D, into the 2D images. And this kind of the idea can be effective in the case that when basically when you have some very dense 3D point cloud, but if we have some very sparse point cloud, obviously there might be lots of the artifacts that we can see in the 2D images. But yeah, actually, people started to work on this kind of like some point cloud representation when you start to see some kind of these 3D scanning devices early 2000, and at that time, many people tried to basically directly use the point cloud representation for many applications. So at that time, people also introduced the idea of like direct point cloud rendering using the software, the idea, which is still used in some kind of the cases, but now mostly people just try to convert point cloud into the mesh or some other representation to use in the many applications. Any other questions for those things? 3D representation. Okay, if there's no more question, we're gonna continue discussing the idea of like some representation, the conversion in the next lecture, in the next Monday. So I will see you next Monday. Okay. Thank you. Bye.